All right. So this week's lab is Lab 14 in your lab book. Okay. So, we have to kind of, you need to read through the labs just like you would in class. All right. But what I'm asking you, I'm not going to ask you to give me all the hundreds of different questions that he asks in there. They are good questions, but it's just, they're good things. So you should read through them. And if you're confused about them, you should send me an email and do that. But the focus of this lab is to build this RLC circuit here. Okay, so if you have your lab book handy and open it up, open up the Lab 14. And I can't tell you what page it's on right now because I've got version 11 of the book, of the lab book with me here. And so I'm pretty sure it's the exact same lab, but it was lab number 12, and back then he shifted a couple of chapters around. All right. So page 426. Thank you, Alex. Okay, so the RLC circuit here, what you want to do is connect it up. So like you say, I would start by taking your original one from last week and opening that up, and then do a file save as, and just save it as like Lab 14 RLC Resonant series Resonant. Okay. And this is just on the same lines as what we've been talking about here for the past week and a half, at least, for RLC or RC filter kind of circuits or resonant type of circuits. And so just working a little bit more with that. So what we have here is we have R, which is 220. So I'm going to change my value there. Just double click on it and change it. So R was 220. L is 10 millihenry. Okay. However, they also indicate in here, because, and I've spoken about this in class, you cannot build a perfect inductor. Okay, all inductors are coils of wire, which means they're going to have some resistance in them. Oops. Okay, so I'm going to change this label here. This is the R. I'm just going to type in IND for inductor. Oops. Okay, and the value of that, then I'm just going to say make it 10 ohms. Okay. All right, so what we've got here is we've got a 220 ohm resistance in the circuit, and then we have an inductor and the inductor here has 10 millihenries worth of inductance plus 10 ohms of ordinary resistance. Okay. And then I'm going to pop this off of here. We're going to have a capacitor. Okay. And so I want to just paste a capacitor, and the capacitor they give us is 0.1 microfarad. So 0.1 U. You can just type those numbers in. A U is micro, M would be milli. Okay. And so you just type those in there, and then I'm going to close this and rotate it. Okay, and so this is the RLC circuit here. Okay, and so, you know, we've got a resistance, we got capacitance, and we've got inductance. And so we're going to take this probe here, and I'm going to put this probe here and measure this phase angle, which is the phase angle from the source, okay, divided by the capacitance, and then you can shift it around or whatever. But this is our circuit. Now we got to figure out what is the resonant frequency. Well, I already kind of talked about that. Right, so remember that we have the inductance is 10 milli. The capacitance was 0.1 e to the minus 6 micro. And so the resonant frequency, I like to use sub R there. The book uses an S for series resonance, okay, but is 1 over 2 times pi times the square root of L times C. Now remember, if you're calculating this, whether you're using the octave program like I am, or you're using your fancy TI calculators, you need to use parentheses around there or you're going to have the wrong answer. Okay. All right, my L was too big, way too big. The L should be minus 3 millihenries. I have 10,000 henries. That would be the size of, I don't know, my house or the school or something. I should be millihenries. Okay, so L is 10 millihenries. Okay, not 10,000 henries. Okay, so like the beauty of using octave is you can just use your up arrow keys and recall those. All right, so the critical frequency here, or resonant frequency, is 5,032. 5,032. All right, so now we can yeah, and round up. Well, we're going to go to 3 significant digits. Right, so at 3 significant digits, if we're putting this as 3 significant digits, it's going to be 5.03 kilohertz. Okay, that would, you know, that would be what we would be putting in Blackboard or whatever. Okay, so all right, so anyhow, I'm going to come over here now at my frequency. I'm going to change my frequency to resonant frequency, 50, and, you know, I mean, you can actually do 5.03 K here for your frequency, okay? And now, before I simulate this, though, you can, there's other meters we can run. If we come over here, we can do the probes, or we can come over here to like multimeters, and we can kind of connect the meters up here. Okay, and these meters, you notice here, if I go to properties, I'm going to call this VR. I think I can rename this. Can I rename this? Thought I could name it. I don't see a label on here, but all right. So, but anyhow, we can come in here and we can kind of put these meters here. This isn't going to give us the phase angle, but if you look at the lab isn't really talking about phase angles. Okay, so you can use these little meters here if you want. And because the nice thing about these meters for this particular lab, they allow us to get the, just double click on them and you pop that open. Now when you open it, we want it to be on voltage. So you see how the voltage is highlighted? But then you also got to click on the sine wave to tell it we want to measure AC. Okay. And then I don't think there's really anything we need to do on the set. Everything they have should be plenty fine for that. All right. So, but now I hit play and you can see the voltage here. Okay. So you can see the voltages. Okay. Now I was putting in 5 volts. I forget, I didn't set the magnitude of my voltage. They had 8 volts peak to peak. Okay. They have 8 volts peak to peak. These things are actually reading RMS. Okay. But honestly, for this lab, we can just come over here. This thing's putting out RMS. Okay. So we can just come over here. Let's just say it's 8 volts RMS and we'll pretend that it's peak to make the lab happy. Okay. All right. And so that you can see here the resistance. You might be wondering why is it 7.6? Well, remember there's resistance over here. So let's take a look here. I'm going to take this resistor out of here. And I'm going to put it on the other side. Okay. So I'm going to paste this resistor on the other side. Now, what I'm going to do with this probe is I'm going to run this probe to the other side, so it's including both of these resistors. Okay, so if we include that resistor, which really in a real circuit we can't separate it, but in Multisim we can simulate this. Okay, and so you see what happens now if I move this and included both of those resistances in there. You see it's actually giving me 8 volts. Okay. But if we just measure VR, if we just measure the voltage across the resistance, which is what is the only thing we can do in the lab, it's actually going to be below that because there's real resistance in that inductance. Okay, so what we're doing here with this is we're simulating this inductance as being a real inductor, so there's some internal resistance, but we can't separate it out because it's through all that copper wire in the inductor. All right, so, but anyhow, so you can see here at this frequency, which is our resonant frequency, the voltage across the inductor is 11 volts. And the voltage across the capacitor is 11 volts. But we're only putting in 8 volts. We're only putting in 8 volts, but we're getting 11 volts in our inductance, and we're getting 11 volts in our capacitance. Okay. And so this is that point that we talk about when we talk about resonance. When you have resonance, you get this inductor. I've talked about it before, but you've got this inductor, you've got this capacitor, and they're basically playing hot potato here, passing back the energy. Right? So the inductor is storing energy for half of the cycle. And during the second half of the cycle, the inductor is dumping his energy, but the capacitor's catching it and storing it up. And so at resonance, we see here that the resistor is dropping effectively the 8 volts. Okay, so again, if I put it across both the resistance of the resistor and the resistance, and I include that resistance, do it one more time here to include this resistance for the, let me change the color of that. You can, if you right click on these, you can go to segment color and change the color. I just like to do that once in a while just to kind of indicate that. So you can see this, right? If I include both the separate resistor and the resistance inside the inductance, right? The resistance in the circuit is dropping what the voltage is giving us. But these two guys over here are sitting here playing hot potato, passing energy back and forth and back and forth. And that's this critical thing about resonance here. These two are just sitting there passing this energy back and forth between each other. All right, so but in the lab, they're asking you to just measure the resistance here at the of the actual resistor, because that's what we, and if we were actually in the classroom measuring it, that's the only resistance we can measure. Okay. And so it turns out to be a little bit less. Okay. Now, if we go to part 2 in the lab, in part 2 of the lab, they changed this 220 ohm resistor to 33 ohms. And watch what happens when we do this. Okay, so now when we do this, we've got 6 volts here. And again, the reason that's 6 volts is because this is 10 here. If I was to connect this over here, we would be getting the 8 volts across all the resistors. But look at this. I'm getting almost 60 volts. I'm getting almost 60 volts between at the inductor and the capacitor here, because these guys are sitting here playing hot potato and there's very little resistance, right? We dropped that resistance from 200 down to 33, okay, but actually it dropped from 230 down to 40 is what it did, right? Because there's 10 ohms here, okay? And so, but you see this hot potato thing going on here. This is a pretty active hot potato game. All right. I mean, if you wanted to drop it some more and drop this down to 10 ohms, this is just to see what happens. Right. Now we're putting in 8 volts, and yet inside of the, or across the inductor, and across the capacitor, we got 125 volts, 125, almost 100, 126 across the inductor. Okay, almost 126 across the thing. Notice here on the inductor, though, I do have the inductor terminal, including the voltage dropped across this resistance, right? Because again, if we were in the classroom, we're measuring this voltage across both. And that's why the voltage here is higher. If I was to actually take this connector and connect it to just the inductive piece and ignore the resistance, these two would be equal. Well, I guess they're still not quite equal. I guess actually the reason they're not quite equal is I rounded up my frequency, or rounded down. Okay, because as Alex pointed out, it was 3.3 here. So if I change the frequency just a hair, I guess it didn't help there. Okay, but I thought if I shifted my frequency just a little bit, but anyhow, you know, but in reality, what we need to be measuring is the voltage here, because in the classroom, that's the voltage we would be reading. All right, so in the lab, okay, in the lab, like we did last week, okay, we need to build this circuit. Now, there's just the one circuit, and then, but you have R. I use 216 here because that's what they had in my lab book when they physically measured it. So that's why it really should be 220 there. I don't really care if it's the 216 I wrote down or the 220 in the lab book. Okay, it's not going to make a huge difference at 4 ohms. But that's why I had 216 in the lab, because I was looking. I've actually, the lab book I have here is actually the solution manual that they give the instructors, and so they were showing when they actually did it in their lab and they physically measured the resistance, it was 216. So that's why there was 216 there, if you're wondering that. All right, but what we're going to do is you're going to change your frequency, 500 hertz, 1K hertz, 2K hertz. So we just come over here and we're going to stop the simulation, double click on your voltage source, set it to the various frequency, say OK, simulate it, read the voltages. Notice that this voltage is millivolts, okay, and this voltage is also millivolts. So notice that the capacitor's got all 8 volts across it, okay, and so then you're going to come over here in the lab and just record those values. Okay, so you've got, if I can get them both on the screen here. That's why I need dual screens. I hate working with a single screen, but we're just going to record these values. So the capacitor is 8.08 volts. And the inductor is 84. You may want to kind of rearrange them so that they're in the order of the table. Just keep, you know, just keep straight which is which. I wish you could label them. Maybe you can. I just have to look harder. All right, but the inductor is the 84.2 millivolts, and the resistance is 25.5 millivolts. And then from there, we're going to calculate the current. Okay, remember Ohm's law tells us that the current I is the voltage across the inductor divided by the current through the voltage across the resistor divided by the current through the resistor, right? Or by the resistance, I'm sorry, is Ohm's law. And then you can calculate your impedance using E divided by I and just fill out this table. And then once you've filled out the table, you go to part 2, and in part 2, you're going to change it to 33 ohms. Okay, so which I just showed you. This was actually with 33 ohms here, because or actually it was 10 ohms. I never changed it back. It should be 220. Okay, and you'll get this message when you, if you're still simulating, you need to stop and restart to simulate it. Okay, but go through there and fill out the tables that are, you know, the tables are in your book, but you just need to fill them out in the lab. Okay, so in the lab here, fill out these tables, and then you need to do the plots. So I've got the plots here for you. So like we did last week, you can click on the plot, type Control X and delete it, and open up the Paint program, paste it into Paint, and then plot your points. Okay, so just come over here. I kind of recommend to plot a point. You're going to want to like pick a symbol. Okay, so for each one, choose like a different symbol. So they have these like shapes and things down here. Here you can use like a diamond and maybe use a different color. Okay, and come over here, and so when you're plotting your points, you just plot your points for your VR. Okay, whatever they are, I'm just dumping some points in here right now. And then we're going to go to the pencil here and draw a line through it. Okay, and show that your, I know it's kind of hard. I'm not going to be too hard on you here if your lines are a little bit wild. But notice if your line's like really bad, if you're like, oh, like that, you can do a Control Z to undo it and try it again. All right. So, and then when you want to plot VC, change your color and change a symbol. Go to a different symbol. Okay. Or a different shape or something. Star. Try to make them about the same size, but okay. And then go to your freehand and draw in a different color. Okay. And then you can label this. You can come over here and you can label this. This was your voltage across your capacitor. Right. And then go back to your other color. And this was the voltage across the resistor or whatever. All right. But just plot, do those plots. And then you can do a Control A here to copy all of this. And then Control C, Control A selects everything, A for all. And then Control C to copy it. And then come back here and paste it back in the document. Okay, so you paste it back in your Word document. You're going to save this and upload it into Blackboard for your assignment. So this is our lab for today. Okay. So is there any questions about the lab? Okay, so I did record this so you can come back and go through this again if I went a little fast. All right, but we're going to build up the circuit. So we're going to build up the circuit, simulate it, get your values. Okay, and like I say, we actually have the capacitor. When you look at the table, it's got the capacitor voltage first, then it's got the inductor voltage, and then it's got the resistor voltage. Okay, so just make sure you keep straight which is which. And the other thing is, this voltage source, it's asking for RMS, but the lab is saying peak to peak. Remember that it's just a scaling factor, 2 square root of 2. So if you just set this to 8 volts RMS, and then these guys are reading RMS, okay, so you can just read these values and record them. So, you know, stop the simulation, change your frequency, and put the values, you know, do your next values. Okay. All right, so that's it for today's lab. Any questions there? It doesn't matter what order. So if you want to put your capacitor first, and then your inductor, and then put the resistor over here, then they would be lined up like they are in the circuit. I just didn't line mine up in the circuit like he did. I did draw the circuit like he had it though. So, all right. Wednesday. Yeah, I guess this lab's probably going to take you a little while, so we'll just have lab day on Wednesday, so you don't necessarily have to log in.